The last application we're going to talk about, the last application to integrals that we're going to talk about is differential equations. Now, a differential equation it's an equation. Imagine that. It's an equation with derivatives in it. Now, there are all sorts of these because there are all sorts of derivatives. So you can have regular derivatives, you can have second derivatives, you could have fourth derivatives, you could have combinations, or you could have partial derivatives, which I know you haven't gotten there yet, but in Calc 3 you talk about taking derivatives with respect to a certain variable when you have multiple variables in an equation. But it's just an equation with derivatives, and these come up a lot in engineering, and solving these comes up a lot. So here's an example of a differential equation. Let's look at, we could say y times y prime plus 4x is equal to 0. It's an equation, it's got an equal sign in it, and it's got a derivative in it. So that makes it a differential equation. Now, solutions to differential equations, it is the dependent variable. So solution is the dependent variable that when you plug it into the differential equation, it makes the equation true. So the dependent variable in this is y, because we have y prime, and that's a dy dx. It's saying that y is dependent on x. So x could change, it's independent, but whatever you get for x, you will get something for y, and y is dependent on that. So basically, the variable that you're taking the derivative of is the dependent one. And so that's your solution. So the solution is a y value. It's a dependent variable, and a solution to this is root 12 minus 4x squared. That is a solution to this differential equation. And I'm going to show this. So I'm going to show it's a solution by plugging it in. So I'm going to plug in y for y, root 12 minus 4x squared. Then for y prime, so for y prime right here, I've got to plug in the derivative. So that times y prime, so let's see, 1/2 has to come down in front, and then a root of 12 minus 4x squared is going to go in the denominator. And then I have to multiply by a derivative of an inside part. So I'm going to multiply by negative 8x. Then, I'm going back up to the equation here. I've got a plus 4 times x equals 0. So in this equation, I plugged in y. I was plugged in the y that was given, our solution. I plugged in the derivative. I had to find that. And then I just kept going with the equation. I added 4x equal to 0. And let's see if this is true. Okay, so if let's see, I've got a root in the numerator and a root in the denominator. Those will cancel. And 2 goes into 8 4 times. So then I'm left with negative 4x on the top plus 4x, and sure enough, that equals 0. And so what that means is that y equals root 12 minus 4x squared is a solution to the differential equation y times y prime plus 4x equals 0. This is a little unintuitive. You guys are used to taking functions. You guys are used to taking a function like this and then finding its derivative in some way. So it's a little unintuitive to get an equation with a derivative in there and then go backwards. So, and here's where the integration will come into play. But first, I wanna look at one other example of just kind of solutions and a differential equation. So let's see if y equal to the sine of 4x is a solution to y double prime equals 16y. So we're going to plug in that y into there. So we can plug in y, that'll be fine, but we need to plug in a second derivative. So let's find that. Now the first derivative of sine is cosine. And then we'll have to multiply by 4 because of the derivative of the inside part. And the second derivative, 4 times 4 is 16, sine of 4x, and the derivative of cosine is negative. So if I go back to this equation and I plug in the second derivative is negative 16 sine of 4x. Is that equal to 16 times y, which was sine, sorry, that's kind of a mess, sine of 4x. Does that equal? And no, because of that negative sign. So if you carried this through, so if you canceled, divided by 16 on both sides, you could divide by sine of x on both sides, but you'd get negative 1 equals 1. That is definitely not true. And so, no, this is not a solution. So that y value ended up not being a solution to the differential equation. I just wanted to give you an example of what it looks like when it ends up not being a solution. You end up getting some sort of a contradiction in there. Okay, so now what we're going to look at is solving these. So there are certain forms that we can solve. So we can solve, meaning that we can find a y value. And they look like differential equations, so a dy, say a dx, where you can separate the function of y from the function of x, and those can be multiplied together. And these are called separable. Now there's an entire semester on differential equations because there's lots of different methods to solve these depending on what they look like. But if they look like, if they look separable, so if a function of y multiplied by a function of x happens in the derivative, then you can separate it, meaning you can get all the y's on one side and all the x's on the other. Equals g of x dx. So all y's on one side of the equal sign and x's on the other. You're then going to integrate both sides. So here I can even put these with steps. 1, get all the y's on one side and x's on the other. 2, integrate both sides. Integrate both sides. And third step, if you can, you want to solve explicitly for y. And what this means is that you're going to get y equals, and you'll get some function of x. And because of integration, you're always going to end up with a c in there. So I'm going to put a fourth step to this. And that fourth step is to solve for c if you're given some sort of extra conditions. A lot of times we call these initial conditions. So an example would be like y of 0 equals 2. So that would tell you that, I'm just going to say missing either. So that would tell you that in this case, when x is equal to 0, y is equal to 2, and you could plug those in and solve for c. Okay, so let's do an example. So let's solve dy dx equal to e to the y times square root of x. So notice how this is a function of y times a function of x. So the first thing we're going to do is get all of the y's on one side. So we're going to divide by e to the y. And we're going to get all the x's on the other. All right, so now we want to integrate this. So I'm going to rewrite this as e to the negative y dy. And I'm going to rewrite x as x to the 1/2 dx. I'm just kind of getting ready to integrate these because I know with x I want to do a power rule. With that e to the y, I need it in the numerator. All right, so now second step, I'm going to integrate both sides. The integral of e to the negative y is negative e to the negative y. And the integral of the square root of x is x to the 3/2, and we've got to multiply that by 2/3. Now we have two different integrals. I always just add the c to the right-hand side, because say you wanted to add c over here, well then just take it and bring it to the overside and combine it with that c. So just write it as 1. And I always write that on the right-hand side. All right. So the next thing, the third thing, is it said to solve for y. Okay, so we need to try to get y all by itself. So I'm going to first multiply by a negative to get e all by itself. So e to the negative y is equal to negative 2/3 x to the 3/2 plus c. And I should explain here, I actually made that a plus c on purpose, because that c at the end is just a constant. It's just something that's there, and we haven't solved for it yet. So even if it were a negative, it would still just be then some number. Even if I multiplied it by 2, it would just be some number. And so I'm calling it c again, even though I know it's a little different. And if it bothers you, then just put a little c1 there. Say it's a little different, because it's not going to matter at the end of all of this. All right, next I'm going to take the natural log, because now I have e. So if I take the natural log of the left side, I get negative y. If I take the natural log of the right side, well, I get natural log of everything that's on the right side. And then I multiply by a negative. So y is going to equal the negative natural log of negative 2/3 x to the 3/2 plus c. Now in this example, I didn't give you any initial conditions, so that fourth step, you don't need to do it because there was no initial conditions, no saying what x would equal when y equals a number, etc. All right, but let's do another, and I want to do two things with this example. So differential equations are highly useful in engineering because it's really nice to be able to write out. There are lots of times when we get formulas for things in terms of their rate of change. So we could say, and this is just an example, the rate of change of population, let's call it capital P, is proportional to the population. So what this is saying here, we've got the rate of change of population P. That's a derivative. It's a derivative with respect to time. And there's lots of applications and lots of places, especially in engineering, where you have things changing over time. So this rate of change of the population is, now in math, that's an equal sign, proportional Proportional in math means we're going to multiply by a k. If it was inversely proportional, it would be like 1 over. To the population, proportional to the population. So the equation that we get, the differential equation that we get is dp dt equals k times p. All right, so let's say that we start out with a population at time 0 is equal to, I don't know, let's just say we've got 100 of whatever we're talking about here for population. I'm feeling fairly uncreative right now, so we've got 100 things, and so let's solve this equation, and let's say also that k is equal to, I don't know, I'm going to choose 3. So our differential equation is dp dt equals 3p. Now, different species have all kinds of different growth rates. This k is a growth rate. What I'm saying is that it grows, so proportionally to the population, its growth rate is 3. I think the human growth rate is like 2.7. I don't know, this is just off the top of my head right now, but I think that's approximately what it is. So each different population has a growth rate. If the population is declining, then that k would be negative. Okay, so just a little bit of other background here, but now let's go to solving this. So we're going to separate it. So we want everything with p on one side and everything else on the other. Now there's 2 different ways I can do this. I can divide by p and leave 3 on one side. I think that's a little bit of an easier way to do it. But you could divide by the whole 3p and then leave 1 on the right-hand side. I'm going to integrate both sides. So integral of 1 over p, that's natural log p. And integral of 3 is 3t, and then I'm going to add that c to the right-hand side. So now when I solve for p, I need to exponentiate both sides. So p is going to equal e to the 3t plus c. Now here's a little bit of I'm going to use some exponential rules here. This is the same thing as e to the 3t times e to the c, because you would add exponents. But I'm going to call e to the c, I'm just going to call that c again. In the last problem, I called negative cc. E is 2.7 something, and c is just going to be some number, so let's just call that c. And so what we get out of this is that p is going to equal ce to the 3t. It puts that constant, I just put the constant out in front. Okay, so once again, that's a little bit tricky, but what I'm doing is I'm taking e, it's a number, c is a number, so e to a number is a number, and I'm just calling that c again. If it bothers you, call it k. Either way, it's just going to put a number out in front. All right, so now I have p equal to ce to the 3t, and now I want to apply that p of 0 is equal to 100. And what this is telling me right here is that at time equals 0, so when we start whatever the study of this population, we start with 100 people or things or whatever we're looking at. So p is 100. So I'm going to plug those 2 things in to this equation. When p is 100, ce to the 0, e to the 0 is 1, so this makes c 100. And so the solution to this differential equation is p equal to 100 e to the 3t. All right, there is much more that we could do with differential equations. Obviously, there's actually 2 semesters on it even. So this is just kind of a brief introduction into differential equations and what you can do with them.